Okay, so guys, Assalamu-Alaikum everyone. May Allah peace be upon all and each and everyone who are connected with us within the Pakistan and out of the Pakistan as well. Now, let me introduce myself that this is Muhammad Shahbaz, who are undergraduate student of NED University of Engineering and Technology, pursuing career in a data scientist and artificial intelligence.
பாகிஸ்தான்ல நடக்கிறதா இது? பாகிஸ்தான்ல நடக்கிறதா?
And right now, I'm really enthusiast of quantum computing. So today I'm your host as well. So let's come to the point, and without being further delay, let's get to it that why we are today here. We are here to know about the most sexiest technology we have in 2020, that is quantum computing. Okay, so let's move further and start our session. That what is quantum computing actually, and what we are going to learn today. If you think that you all have been born from your old classical quantum computing, there are many people who want to in. Let me see first, because for being hot, it's really typical. Have you all been bored from your old classical computers, right? So let me tell you one thing, that you are not only one who have been bored from all classical computers. Most of the world computer scientists, engineers, and experts are already bored from all classical computers because of their complexity power. Because we are living around the edge of technology where we have everyone data, and for processing the data, we cannot. Our classical computer cannot do this anything at all. So we need to forward now. So get rid of your all classical computers because the future of technology has arrived. No, I'm not talking about the artificial intelligence, because artificial intelligence without data cannot do anything. Neither I am talking about the virtual reality that interests you in the world of dream, because it also requires a good communication computational power. I'm talking about something different, which is the most access technology of future, that is quantum computing. Now, that is another thing, that what is quantum computing and on what principle quantum computing works, how to build a quantum computer. Is there anything who can already build a quantum computer? You will get to know all answer in a couple of hours. Yes, it's fact the quantum computer can change whole world. It makes changing in all fields, either our way of living, our mindset, and everything, right? But let me tell you about some interesting facts, some application. Medical sector. If we have quantum computer today, so we can easily find out the solution of coronavirus. The finance sector will also going to be easily solved, like it's a credit risk prediction and finance. And one more thing, the cyber security. As we know that the internet have no boundaries, so everybody can harm your security. But after having a quantum computer, no one can harm your security. No one can enter you in your system. Hacking will not be possible. So what is quantum computer in actual? We need to find out then. And the most important thing, that how does it work? On what principle it works, right? And further, on what principle it works, and the most important thing, when can we expect it? Is in the future it will build or not, or is there anyone who can already build? And the most important thing, what happens if it gets in the wrong hands? Because if the wrong person can make a quantum computer, that he will can easily damage all the world without one click, because of a just quantum computer. So let me tell you something about today's session. Obviously, you are excited to learn about the quantum computing, but let me tell you that we are a group of students of people right now. Our society, because we are the part of NED University and we are the students there, and our society quantum computing club is not registered there. right? People right now, and our society computing club is not registered yet. And but we want to share our experience and achievement that we got recently in IBM Quantum Challenge 2020. We are considering that you are an intermediate state of quantum computing. So what our mission? Our mission is spread to knowledge about quantum computing, build a group of students who can work on quantum computer, and starting to build a quantum computer and its function and make a design and a practical implementation. Okay, so let me call you the first speaker we have today who will enlighten you on quantum computing, and that is we have Iqra Naz. And in the next session, and the next time, the Iqra Naz we're going to have you. Okay, so you need to wait for a while. I'm going to transfer the call and I'm going to change the host. Okay, Ikra, the time is yours. Ikra, can you hear me?
Yeah, I'm here.
Perfect.
Just a minute.
Sure.
Um, okay. Assalamu-Alaikum. Good afternoon and welcome to the webinar by Quantum Computing Club. बेसिकली जब हमने जो है वो अपने इस क्वांटम चैलेंज के डिफरेंट स्टेटस लगाए ग्रुप्स पे लाइक सोशल मीडिया पे, इसके अलावा जब अपने बैजेस अपलोड किए तो सबसे ज़्यादा जो क्वेश्चन था मेजॉरिटी जो पूछ रही थी वो ये था कि व्हाट इज दिस, ये क्या है, कैसे है, एंड सो ऑन. सो हमें ये लगा कि हमें जो है वो इसकी इंफॉर्मेशन को जो है वो बहुत ज़्यादा पब्लिक करने की ज़रूरत है, क्योंकि ये टेक्नोलॉजी अभी भी बहुत ज़्यादा पॉपुलर नहीं हुई है. सो हमने ये वेबिनार इसलिए अरेंज किया ताकि हम जो है वो अपने क्वांटम कंप्यूटिंग के नॉलेज को जो है वो डिलीवर कर सकें, और इसके अलावा हम अपने IBM क्वांटम चैलेंज 2020 के एक्सपीरियंसेस जो है वो आप सबके साथ शेयर कर सकें. फर्स्ट ऑफ ऑल, ये चैलेंज जो है वो IBM क्वांटम एक्सपीरियंस की 4th एनिवर्सरी पे लॉन्च किया गया था. दैट वाज 4th May 2020, and it was a challenge of 4 exercises and for 4 days. Globally thousands of participants ने जो है वो इसमें पार्टिसिपेट किया, और फिर उनको जो है उनके टास्क कंप्लीशन लेवल के हिसाब से बैजेस भी अवार्ड किए गए. एंड अल्हम्दुलिल्लाह we 4 participants from Quantum Computing Club got advanced badge. So let's start इस उम्मीद के साथ कि आज आप क्वांटम कंप्यूटिंग के कुछ बेसिक्स कॉन्सेप्ट सीख सकेंगे, और नेक्स्ट टाइम आप भी इस तरह के कॉम्पिटिशन्स और चैलेंजेस में पार्टिसिपेट करेंगे. बेसिकली इस चैलेंज में 4 एक्सरसाइजेस थे एंड इनकी जो ग्रेजुअली इंक्रीजिंग डिफिकल्टी लेवल्स थे. फर्स्ट एक्सरसाइज था क्वांटम गेट, then measurement error mitigation.
Excuse me, ma'am.
Yeah.
Ma'am, could you please talk in English, ma'am, because we can't understand your language. Hello, ma'am.
Yeah.
Ma'am, could you please talk
Yeah,
in
of course.
English, ma'am? Because we can't understand your language.
Okay.
Yeah, ma'am. Thank you so much.
Sure. It comprises of 4 exercises. First exercise was quantum gates, then measurement error mitigation, quantum cryptography, and then the last and final challenge was circuit decomposition. So we will discuss all these exercises one by one. So before proceed further, I want to introduce other speakers of the webinar. I'm Iqra Naz from ND University of Engineering and Technology. I'm an undergrad student of Software Engineering Department. Our host Muhammad Shahbaz, who was the student of Computational Finance Department of the same university. And our first speaker is Muhammad Miqdad Khan, who will explain the quantum computers and its importance and quantum gates, etc. He's also the student of ND University, and he's from Applied Physics Department. Our next speaker is Rubab Manzar. She is also from Applied Physics Department, and she will explain you measurement error mitigation. And then Muhammad Mooazam will explain you about quantum cryptography. He's an electrical engineer. He's from electrical engineering department. And then in last, I'll explain you the quantum circuit decomposition. So, hand over to Muhammad Miqdad Khan.
Hello, Assalamu-Alaikum. Hope you all are fine. Okay, let me start. Iqra, please give me the access of screen sharing.
Yeah. Miqdad, please start. I'm just giving you access.
Okay. Okay, my name is Muhammad Miqdad Khan, and I am a student of physics at NED University of Engineering and Technology. My given task today. Okay, my given task today is to introduce yourself about quantum computer, what is quantum computer with its basic knowledge, and the first exercise of the IBM Quantum experience. Okay, I'm sharing my screen now. Can you see my screen?
Yes, sir, it's visible, sir.
Okay, thank you. So we will
Thank
start. Uh, so we will start with what is quantum computer. So, what is quantum computer? Quantum computer is a device which uses the laws of quantum mechanics to do the tasks of computing. So I just named the quantum mechanics here. So what is quantum mechanics? Quantum mechanics is the study of the behavior of the subatomic particles. So what we understand now, that what is quantum computer? The quantum computer is a device which uses the laws of quantum mechanics. It means that which uses the behavior of subatomic particles to do the computing tasks. Okay, if I talk about the history of quantum computer, then once upon a time, Feynman says that if that I think I can safely say that nobody understands quantum mechanics, but it's not the end. In 1982, Feynman also proposed the idea of creating machines based on the laws of quantum mechanics. Means that based on the quantum mechanics, यानी कि वो सब behavior of the subatomic particles. And then 1985, quantum Turing machine was happened. And in 1994, Peter Shor come with the quantum algorithm. And amazingly, he is alive now. You can also contact with him and learn with him. And then 1997, Love Grover, which is an Indian scientist, developed the quantum search algorithm.
Sir Miqdad, may I say something?
Yeah.
Miqdad, sir, please make it that Rubab can be entered in this session. Please,
Okay.
the
I'm
waiting.
okay. I'm admitting all.
Okay.
Okay, admitted. Okay, that was the history. Then I discussed that why we need quantum computer. So if we look at the Moore's law, then we see that number of transistor on a single chip is increasing every year by doubling itself. So we can easily see by this graph that in year 2000 we have the limit of 100 million transistors on a single chip, and by the year of 2020 we will achieve the quantum limit. अभी हमने एप्पल को देखा. We have seen the Apple right now. That they announced that they will develop the gates with the arm of transistor of 5 nanometer. 5 nanometer is the last limit of classical development of chips. It is already the quantum level. So we need the quantum level right now. Acha. Uh, that's why we need the quantum computer. So how the quantum computer normally work? Classical computer works on the basis of bits, and quantum computer works on the basis of qubits. So what is qubit? Qubit is like a bit in the sense of input and output. It gains the data in the form of 0 and 1 like bit, and gives the output in the form of 0 and 1 like normal bit. But in the processing, it is something other. It works on the behavior. It works on the principles of superpositions and entanglement, on the laws of quantum mechanics, which makes them superly fast, even makes them fast than supercomputers what we have right now. If we do some work on the normal computer, it takes years, and if we do that work on the quantum computer, it will do minutes. And in the security sense, like Shahbaz discussed many of the applications, these all we can do on quantum computer, like COVID-19 problem, we can easily solve by the usage of quantum computer, as we can easily gain the knowledge of the proteins and the genetics and genes of the COVID-19, and we can easily find the solution of that. Okay. Acha. I might hear you that I might sound like you that quantum computer is the killer of the classical computer. No, this is not the thing. Classic quantum computers are not the killers of classical computers, as these are the special computers, because special computers, so they are not good in the general computing tasks, like they are not good in the pixel arrangement of the images, etc. So that's why they are not killers of the classical computers. Okay, let me proceed to the our first challenge. Wait a minute. Okay, my screen, my new screen is visible to all of you. Shahbaz, can you?
Yes, sir, it is visible.
Okay. So this is the first challenge of the IBM's challenges, that is introduction to Qiskit. In this challenge, we have to make some of the gates and with working with it. I wish I can explain from the website of IBM Quantum Experience, but it has been removed from that website because it was only for 4 days, and that's why I am explaining it with my GitHub. Okay, so it is the first exercise. In this, they introduce the Qiskit, and we have to work like there is complete all knowledge here. I uploaded on my GitHub. Shahbaz will send the link in the chat. Okay, in the first cell, they in cell में हमें they already import some basic libraries which are needed in this section. So we have no need to हमने इधर कुछ नहीं किया. We have no need to do anything here. Then they introduce some basic operations of the quantum computer here, like writing down single qubit and the definitions and some mathematical functions, and then visualizing the quantum states like phase shifting and angle shifting and superposition, etc. Like this is the example of superposition which we can achieve from the using of Hadamard gate. Acha, I name here the Hedmund gate. Hedmund gate is the basic gate and the very important gate of the quantum computing. It is not like the classical computing gates. It is another gate which is especially built for the quantum computing gates, quantum computing, and it makes the qubits in the in the form of superposition. What is superposition here? Superposition is the state the uh, where the qubit is in the form of 1 and 0 simultaneously. Yes, it is possible in quantum mechanics. In quantum mechanics we have the duality natures, and the duality natures we can achieve the 0 and 1 simultaneously. The qubit can be a 0 and can be a 1 and can be a both. That's why the quantum computers are super fast and they do the many work simultaneous. Like if we do the security purposes, then they can break easily, because if I try to break the password of anything from the local classical computer, then it takes many times, because it will try one by one every possibility. But quantum computer will try every possibility in a single time, in a single run, because it can work on superposition. Okay, then this is the visualization of different gates manipulating qubits. Here they explain the some qubits in like Hedmund gate. They explain like Hedmund gate. If we apply the Hedmund gate, it will do the superposition. And X gate, here they mention the X gate. Which, what is X gate? X gate is the analogy of NOT gate of classical computing. Like if the qubit in the form of 1, then it will do in the form of 0, and if it is in the form of 0, then it will convert in the form of 1. Acha. And they here are some other gates as well, like Z gate shifts the 180 degree of qubit phase, and the S gate shifts the pi by 2 radians, or 90 degrees in the anti-clockwise. S gate do this, and this is the S dagger gate. Like this is the sign of dagger, then S dagger is the inverse of S. Like it will do the phase shift of 90 degree in clockwise. Okay, in cell 2 they produce the mini composer for this challenge. Especially it is not available on Qiskit or Chasm simulator on IBM's website. In normal conditions, it was only available for the for this challenge. By when we run this cell, it gives us the mini composer. Like with the help of that composer, we with the help of that composer we can build a basic gates on qubits, then perform the task. I guess it is not showing in the GitHub right now. Okay, in the cell 3 we have to achieve this condition, which is visualizing here, this form of qubit. So in normal qubit form, the qubit is on the state of 0, and in this form it is on the state of 1. So we can easily achieve this thing by applying the NOT gate. So we do the some coding here. And code was occur in the when we draw the circuits on that mini composer. Then it gives us the code, like define it. We have define create circuit function, then QC equal to quantum circuit 1. Quantum circuit 1 means it is working on the single qubit, not more than 1 qubits, or we can say that it is working on the line 0. Like in programming, we start the counting from 0, and then qc dot x0. qc dot x0 means we have applied the x gate or not gate on the line 0 or the qubit 0. Then it return the qc state of qc, then qc equal to create circuit state, etc. All these lines, all these 4 lines was given by the IBM already. Then if if it is matched with the above state, then it will be correct and message will appear, well done, your progress 1 over 8. In the first challenge we have to achieve 8 points. Then in the next exercise or next task was the achieving this state, which is visualizing here. So I discussed the Hedmund gate, which is the gate for the doing superposition. So it is the condition of superposition as the qubit is in the form of 0 and 1 simultaneously. So we just simply apply the Hedmund gate on the single qubit, then it is achieved. And this is the form of see, it is the form of superposition, and it also, this color change also represent that qubit is in the state of 1. Then it means that here we have to apply 2 gates, that is Hedmund and not gate on a same qubit. So we apply here, then we achieve this. And then this is the condition of Hedmund with the S dagger. You can read in my repository and all these things. And the exercise 2 in the challenge 1 was that the dealing with multiple qubits and 2 qubits. Then here was another mini composer. In this mini composer we have to work with 2 qubits. It is also not showing on the GitHub. It was happening in the website of IBM Quantum Experience, but it is not there right now. So then it is the then it is the superposition, or then first task was the superposition with the 2 qubits. Then superposition with 2 qubits will be achieved with the applying of the Hedmund gate at the qubit 0 and qubit or first qubit, and control not. What is the control not gate? Control not gate is for the quantum computing. In the control not gate, we have to apply this gate on 2 qubits. First qubit is the control qubit and second one is the target qubit. If the control qubit is 0, then it will do nothing to the other qubit. If the control qubit is in the state of 1, then it will change the second qubit like the not gate changes. That's why it is called control gate. So we have to apply Hedmund gate on the first qubit, and CX gate or control not gate on the second qubit. Then this will achieve. So this is the circuit visualizations. We have applied the Hedmund gate on the Q0 and the control not gate on the with the control qubit of 0 and the target qubit of 1. This type of circuit composer which is showing here, you can see on the IBM Quantum Experience website on the Chasm simulator. Okay, then this is the another task. For this task you have to apply Hedmund on the qubit 0 and the NOT gate on the qubit 1, and then control not on these with the control qubit of 0 and the target qubit of 1, and the Z gate on the qubit of 0. Then we will achieve this. This is the circuit visualization, and these are clocks and measuring elements. Acha. Okay, in this cell 10, IBM teaches us that in quantum mechanics we have many possibilities. Like normally we did not achieve the exact thing in the first run, so we have to apply multiple shots. Like here you can see that result equal to execute shots equal to 1000. Here it is showing that we have to see the results in the form of possibilities and in the form of histogram. And this is the all other signs. And we in the quantum mechanics you have to study the quantum mechanics for this, and plot histogram we have to we have see this. And then another task was there, that is the achieving this thing. For achieving this thing we have to apply the rx and swap. And for this we also apply the swap function. Swap function is like regular programming, normal computing programming. We normally use the swap function, so we just like use the swap function here, and then it is achieved. And this is the thing. Then the final task of the first exercise of first, or you can say the first challenge, was the achieving the superposition in the 3 qubits. For this, this is very easy. You simply you have to apply the head on the third qubit, or the 0 1 2, yani ki third line, and then the cx with the control NOT gate with the control qubit of third one, and the second one is the target, or number 2 or number 1. And then again one more cx with the control of line 1 and the target of line 0. Then we have to apply also here, we have to apply the 2000 shots for achieving the our best results. So like here it is the all completed the first challenge. So this was our solution string. We have to put this string in the answer box of the IBM Quantum Challenge website. So it is the very important string, like these number 104, 52, 197, 109, 65, 114 and 100. This is in reality a message. This message we will discuss in the exercise 4, as it is a very important message in solving the exercise 4. See the cleverity of the IBM. It gives us the hint, but we have to find out this hint in the form of these numbers. Okay, that's all from my side. I'm making a host again to Mr. Shahbaz, then he will sorry, I'm making the host Miss Rubab Manzar. She will explain the next exercise for you, that is error mitigation. Okay, thank you very much. Rubab, you can proceed now.
Okay, hello and good afternoon to you all. And I'll start with my part of exercise number 2. I hope I'm audible.
Yes, you are audible. Keep it up.
All right. So here's my screen. I hope it's visible. Now my topic here is measurement error mitigation. All right. So first of all, I would like to explain what exactly measurement errors are. Well, measurement errors are when we simulate a circuit on a quantum computer. So there are some error noise, because there are noises on the system, and the quantum computer works on the principle of quantum mechanics, where you have to take several shots. Shots are the amount of measurements you have to make. You have to make a lot of measurement of single quantity, and then you have to take out an average of all those quantities. So there are fluctuations, and there are noise that is produced in the measurements. So while making these measurement errors occur, and our task is to mitigate them, to minimize them as much as possible. Now, the graphs which are visible here, they explain the need for the error mitigation. Well, when you talk about an ideal quantum computer gives you ideal results, but it is not in practice possible. It's not possible in the real world. Well, every quantum system has 2 states. Just like classical bits, there are states 0 and 1. but they're not just 0 and 1, they're superposition of these states as well. So when we talk about superposition, they create states such as this. I hope they're visible on the screen, the numbers I'm writing. So these are the 4 states which are likely to be the outcomes of the superposition, but an ideal quantum computer, the outcomes are likely to be 0, 0 and 1, 1. There is no chance of 0, 1 and 1, 0. However, it is acceptable in the real world, but in ideal system, it is not in ideal system it is not required that these two states also occur. These two states are important, which are also here 0, 0 and 1, 1, and these outcomes are for the ideal quantum computer, and that is completely acceptable, but it is not possible physically. Now coming to the real quantum results, talking about real quantum results, there are all these states occur and this system is acceptable. There are not any errors yet in any of these systems, but this is much more acceptable than this one, and this one is practically possible, the real quantum result. Well, errors are still not here. Let me explain you what errors actually are. This thing can lead us to the errors. It leads us in a way such that suppose there's a 2-qubit system and there are 4 states as I mentioned before, and they are supposed to give outputs such as this. They are supposed to get outputs a 0, 0 result at the 0, 0 vector, at 0, 1 result at the 0, 1 vector, and respectively the others. But in case of noise, the results fluctuate from the value, and the 0, 0 becomes something like 89 or 9828 or 82, something anything near that 0, 0, and 0, 1 fluctuates from its value. The graph fluctuates. I'll show you the graph as well. So this is the cause of the noise. You can see like this is a 5-qubit system in which their combinations are shown in the x-axis and the probabilities are shown on the y-axis. Now in this system there are noises. The desired value is occurring at 10101 and 0000. Rest is the noise. Rest are the values which are fluctuating from the original value. Now we need to mitigate this. We need to minimize these unnecessary unwanted values as much as you want, so that we get the 2 desired value which are most likely to be comparable with the ideal quantum computer. So we need to minimize these outcomes as much as possible. Now this is a graph which is after mitigation. The pink bars indicate the readings after the mitigation. There are no errors in the pink bar, and the blue bar indicates the error with the mitigation. There are errors in the blue one. So what's the difference here? The difference is that in case of the pink, you can see the bars here are minimized. There are only 2 to 3 pink bars, whereas there are more blue bars here. So after mitigation, this area has become less, and the probability of the desired value at 10101 has been increased, and at the 0000 has been also increased, and the rest are mitigated. But you're seeing that there are still some values occurring here. Well, no system is completely ideal. There has to be some errors, but our job is to bring it close to the as ideal as possible. We cannot make anything completely ideal because that's against the laws of physics. But yes, we can make things as much ideal as possible. So this is the task of error mitigation. Now, right. So now let's understand this thing with linear algebra for any n number of qubits. For example, there's a 2-qubit system in which there are only 2 qubits. So there are 2 n basis states. This means there are 4 basis states. Well, if namely there are 1 and 0 qubits, then there are 4 possible outcomes. All right. These are the 4 states. Now a state, just like I said, we take multiple shots and we average out the value, which is the final result. This is the mathematical form for it. So this is the summation. So this is the summation, and these are the values which are the averaged out, and then the final result is obtained, and this is the value for a system which has no noise, a noise-free system. Now, this one is the equation. This is the equation for a system that has noise in it. Well, now the relation between the noise-free system and a noisy system is through a matrix. This matrix is which is the factor that governs if a system is noisy or not. Well, the relation is such that if we take out the matrix from the noisy system, we are left with the not noisy system. This can be expressed mathematically as if right. This can be explained mathematically. Sorry for my apologies for the inconvenience. So mathematically, this can be explained as matrix inverse of noisy gives us the not noisy state because it's multiplying with it, so it's gonna be multiplied. So our task is to find this matrix and the inverse to find out the not noisy states. So we are going to find, so the goal of the exercise created by the IBM is to create a calibration matrix that you can apply to the noisy results provided by the IBM to infer the noise-free results. Now let's see how it's done. Okay. So our job is to find out the metrics. First of all, the thing that we will do is that we will import everything from the disk. We will be importing our account through which we'll be running it. We will be transpiling it, assembling it, and we will be importing all the tools that are supposed to get us our circuits and run them. So here we just press enter plus shift if you are familiar with the Jupyter notebooks. This will load your data. Then a second task is to find the second task is to find a device that is least busy, because the device you are working on must be least busy, because busy devices give more errors and they take more time in calculation and therefore they produce more errors. So our task is to find the least busy device, and it's up to us to find the least busy device. But IBM has also provided us with the least busy device, which is there in IBM's territory. The device is there with them. We are just simulating that device. We are just loading the device in our computer and we are simulating it. So we are going to call the device that is provided by the IBM. The code is also given by the IBM. We've just got to run this. All right. So this tab will open up when you run this, and it gives all the configuration of the qubit properties and the system we are working on. So it's a 5-qubit system, and we are working on it. It gives the configuration. It's a number of qubits are 5. And then the status is active, right? It's the least busy device. It's not busy, so it will give us least errors. So the calculation will be easier. So there are qubit properties and multi-qubit gates, and there's the error map. This error map is the most important thing. This job history also, but I'll explain what job exactly is. So this is the error map. This is our main focus of attention. Now a third task. So we are initializing things. We have loaded stuff, and then we have selected a device to run our circuit upon, and then we are getting a job watcher. What a job watcher basically is, well, when you are running quantum circuits on your device, your classical computer is basically connected with the IBM's quantum computer. So there has to be a pipeline, there has to be a connection, a link between them. What job watcher does, the job watcher tracks that link, and it keeps the track and returns the value from the quantum computer to our classical computer, so we can simulate. And that ID, which this tab, when we run this tab, it gives this ID, And this tab also appears on our left side. When we click on this, we get the job ID and the name of the system. It's IBM QX2, and the status is done. It's running. The job has been done means that it's running. We have started it. All right. So we get a job ID. Now third task is to get a measurement filter. What measurement filter is? It's basically the matrix we need. The measurement, the matrix is a linear algebraical term, and this is the term, the measurement filter, graphical representation of that in coding. So we have to create this measurement filter, and after running this cell, we get this graph. So there is a dark like diamond shape or square shape line diagonal, and there are some faded diagonals as well on the back. So what do they mean? The diagonal actually means that these are the photons. Basically, a qubit is the state of a qubit is governed by a polarization of photon and spin of electrons. When we talk about classical state, this state of a system is either on or off. It's either 0 or 1. So when talking about similarly about quantum circuits, the qubits also have their states, but they're not on and off. They are the state of photon polarization and electron spin up or spin down. Talking about photon polarization, so the current state is the direction of polarization. So polarized photons are basically the qubits, and this faded area shows the photons which are depolarized. This means they are the errors. So the correct part is the dark diagonal. So through this measurement filter, we are going to get our histograms and compare them and do all the mitigation of the. We are going to remove all the errors and noise from the our systems. So let's see how it's done. All right. So we are given the first exercise. We have to run this cell and we get this histogram. And here we see the output. This is a noisy output where there are probabilities on the y-axis. Now just to understand how this works. Well, these are the probabilities. It's a 0.5 probability at 0, 0, 0. So the desired probability is 0, 0, 0 at 0.45, right? And it's at 111, it's 0.338, all right? And there are errors. Now let's see what happens after mitigation. When we mitigated, the error-free results occur, and those error-free results show that. All right, I want to indicate one thing, that pink part are the error one, and error-free is blue here. All right, blue one is error-free, and pink one is full of errors. So when we talk about the blue one, so when we see that the desired results after mitigation at 0, 0, 0, 0, we get a approximately 0.5, and at 111 we get approximately 0.5. So it's a 50-50% probability of both the results, and the rest are ignored and rest are mitigated. So let's see now. Let me show you. All right. Okay. So after running those cells, these pictures are basically this, right? So after running the cell, and we have to compare the histogram of the mitigated with this, right? So all right, when we see that as 0, 0, 0, and 1, 1, 1, there's a 50-50% probability. Now see which result matches the most. We look at here, we find the 0.2 probability and 0.2 probability, which is nothing near to 0.5. This is not a 50-50% probability because the 100% is distributed over here, and there's only approximately 20% probability here, 20% probability here, rest are over here. So this is not a desired result. And if you look at this is 0.1 and 0.1, approximately 50% probability, and the rest of the probability is distributed here. So this is not our desired result. Now we talk about this. This is approximately 0.6, and this is approximately 0.4, which not at all matches the 50-50%. This is 0.5, and this should also be a 0.5. Well, this result is 0.5 and 0.5 approximately. So this must be true. So our job was to uncomment the answer C. Now similarly, we get the second set of noisy ones. We get the second set of noisy counts and we again mitigated. Now we saw that at 11111 we get a 0.6 approximately probability of the error-free result, and we get at 0.00 is approximately 0.4. Now we have got to match that which result matches the most. Alright, so there's 0.2 and 0.2. This is nothing near to 0.6 and 0.4. And this is also 0.12 and 0.12 for rest of the probability is distributed over here. So it's nothing here. We need a 60%, 40% ratio. And this is a 50-50% ratio, so this doesn't match either. So our correct answer is this one, because this is a 40% of it, 0.4, and this is 0.6, the 60% of it. So the total probability is equal to 1, and which is 100%. So 0.6 is the 60%, and this is same as this one. So after mitigation, we saw that this one is the correct result. So which the matches with this one matches with the correct result. So this is our answer. We have to uncomment the answer D, which I have done this on my Jupyter notebook. Then we are given similarly the third set, and this set, okay, this one is a bit typical. After mitigation, we see that after mitigation, all right. So the pink ones here are the error full of error results, and blue one here are the error-free results. We see after mitigation there are only pink ones. So this is not the error-free result. We are focused on the blue ones. So our first error-free result occurs at this value 00100, leaving the 4 quantities behind. Then these two values are left out, and then we get a value of at 00111. All right, so these major bars, the major histogram with the most probability, we will focus upon them. We will ignore those that are in minorities, because they are just random fluctuations. So now we are going to match which one resembles the most. Well, this one doesn't resemble, because the first 4 values we received, they're empty in the mitigated part, but they're present here. So this cannot be the result. Now coming here, these 4 values are also present, and mid values are also present. This doesn't resemble this at all. There are only 1, 2, 3, 4, 5, 6, 7, 8 values at respective numbers, and this doesn't match. This doesn't match this at all. And this one is also giving initial values, and this one is giving values in between as well. It's not a mitigated result. But this one because it's giving the majority values just like that. It's giving the major values of probabilities, and it's not even giving values anywhere except for these specific numbers. So it's just like it resembles this the most. So we are gonna uncomment the answer B. This is all. All right. Fourth one will also happen similarly. We'll run this cell and we will get the noisy results, and then we will run this cell and we get the mitigated result. But the problem here is that the IBM has removed its challenge from its website, and we do not have the original challenge and the functions which were created by the IBM. We cannot load them here. So they were created in their system only, and we do not know them. We were just solving what we were given. So unfortunately, and that's removed, so I cannot get the mitigated results anymore. So but the solution was just the same. We had to match the result on similar pattern, and then finally we needed to uncomment the answer of that as well, and then we had to run this shell because it had the final answer contained those references to the values of the previous answer. So after running this cell, we got a code, and that code was CBBB, and we were supposed to input that code into the dashboard of the exercise, and our result was submitted. So that's all from my side, and now I'm going to hand it over to Muhammad Mooazam.
Rubab, can you hear me?
Yes.
Rubab, please make sure that everybody get in this session. Many people are in waiting zone.
Yes, I am admitting everybody.
That's right.
Rubab, can you please allow my screen share?
Yes, just a second.
Mosam, please make sure that everyone's mic muted.
Okay, let me see.
All right, Mozam, over to you.
Thank you so much. Okay, now I'll start with my presentation. First of all, Assalamu-Alaikum, guys. This is Syed Muhammad Mooazam. Syed Muhammad Mooazam from NIT University. I'm doing electrical engineering in Pakistan. Now, in this exercise, I will talk about quantum cryptography. So, what is cryptography? Cryptography basically means changing code. Uh, say, we can see it as changing the front end of the code, the text which is shown, which is not the actual. It's coded. It's called cryptography. But when we say quantum cryptography, which means the code is changed uh, by using quantum mechanical properties. The best known example of quantum cryptography is quantum key distribution. The other example is BB84 protocol. What is BB84 protocol? Let's discuss here. These two person named Charles Bennett and Claes Brestrad, they made BB84 protocol in 1984. This was the first cryptography protocol. They both were at IBM company at that time, and they both are still working in IBM. They were the first person to make any quantum cryptography protocol. And now this is the basic of the BB84 protocol. It says that when we evaluate, when the value of k is 0 and the value of b is 1, then we get a answer of 0, which means a horizontal line. And when we have a value of k 0 and b equals to 1, then we have a value of 45 degree from east. And when we have value of k1 and b equals to 0, we have a vertical line value. And when we have k equals to 1 and b equals to 1 2, then we have a 45-degree value from north. This is the basic, and this is used further in this cryptography protocol. Now, the thing we discussed is used here. This is this is an example of BB84 protocol. It says there in here, the value of k is 0 1 1 1 0 0 1. This is pre-decided. And the thing is, b is the basis of Alice. Now, whom are Alice and Bob? Alice is the person who is sending a message. Sorry. Alice is the person whom is sending the message, and Bob is the person whom is receiving the message. So Alice wanted to send a message to Bob. He he cryptographed it and send it to Bob. So how he will send it is shown here. Alice, here the value of b uh, is the basis of Alice. He also pre-decided it is 1101 000, and then from value of k and b we will find Alice prepasses. How we will find Alice prepasses? We evaluate the value of k and b which we discussed here. From this image we will evaluate the value of k and b, and like on the most left it is shown k is equal to 0, b equals to 1. Here k equals to 0, b equals to 1, we get a value of 45 degree from east, and this is what we get here. And same with k equals to 1, b equals to 1, we get a value of 45 degree from north from this image, and this is the answer here. So that's how we will find Alice tree-passes. Now we have find Alice tree-passes. Now it's time to find Bob measures. Bob measures here b dash. This is the value. This is called Bob basis, and it is also pre-decided. Its value is 1001101, and then we will find Bob measures. How we'll gonna find it? We will wait k. On the top, it's the value of k is shown, and we evaluate it from b dash with b dash. From here, the value of k is 0 and b dash is 1. From this image, we will find that k equals to 0, b equals to 1. We get a uh, value which is shown here, which is 45 degree from east. That's how we will find Bob measures. Now we have find Alice measures and Bob measures. Now we will find k dash. How we will find k dash? We will evaluate b dash and Bob measures to find k dash. How we will find k dash? We here see that b dash equals to 1, Bob measures is equal to 45 degree from east. 45 degree from east, b is equal to 1. Here the value of k is 0. From this image we will find k dash. uh, Similarly, evaluating all, we will find all the k dash. So what is k dash? We find the value of k dash as 0011000. Now what we're gonna further do that, comparing value of now we will compare value of k and k dash. Now on the top left, it's 0. The value of k dash is also 0, so it's correct. Now the second from the left is the value of k is 1 and the value of k dash is 0, so it's not matching, so we will neglect this value. Like that, we'll find all the value of k. It's called key. Now the value of key is 0110. So what we're gonna do with this value, we will find next. The value of key here we find is 0110. Now let's move here. This is the main point of cryptography. This is in message encryption and message decryption. Using the protocol BB84, we will do encryption as well as message decryption. Encryption means changing the message into a code, and decryption means changing a code into the message again. And why we gonna do that thing? Because we don't want anyone except the sender and receiver to read the message. That's why we cryptograph the message. How we gonna do encryption and decryption? From this equation, we can encrypt the message by an equation saying that C equals to M XOR key. So what is C? C is the coded message. What is M? M is the message, the real message the sender want to send. And what is the key? We find the key in the previous slide, which is 0110. We have find the key. We have got the message that we want to send. Now we evaluate between them. So the symbol between them is XOR key, XOR. XOR key means it is a normal key which evaluates on that when same bits like 00 and 11 are evaluating, the answer will be 0. And when different bits like 01 and 10 evaluating, the answer will be 1. That's how XOR key goes. Okay, so we find message encrypted key. Then when it received by receiver, he has the key. The key is found as 0110, and he got the cryptographic code. So he evaluate again with the XOR key and will find the final message that the receiver want to send in decrypted form. Okay, now let's head towards the exercise 4. So now it's exercise 3. Here you can see my repository of exercise 3. Why I'm not showing the actual IBM site? Because IBM deleted the challenge, but we saved it as a repository. So we are showing the question and their answers to you. Now I have also mentioned about quantum cryptography. I also told about these two men. I also told about BB84 protocol. I also told about the basic, and I also explain this example with you briefly. I also tell about messaging encryption. Now, what we're gonna do in this? Okay, here. Wait a second, please. Excuse me, wait a second, please. Now everything is fine here. Now in the first cell, we are gonna do measure the bob bits. How we gonna do it? Okay, so all the import function, all the import commands, and all these commands are pre-written by IBM. We don't want to edit it, and we can't. So what the thing we did here is this def. We edited just this def function. Okay, now you are seeing this. It's only if and else command, but it's not that simple. We researched many hours for it, and we finally got the logic to use if and else, where here we are finding bob bits. How we gonna do find bob bits? Here we see in ppt that bob bits can be compared by using the basic image that we also discussed. Here we use def function, bob major key. There are three arguments in it. We use if else function. The comparing method of if is bob basis qubit index means the number of qubits 0 1 2. Here we have only 0 1. Now compare it 1. If it's 1, then add in qubit circuit, otherwise pass. This is basic. Now we measure the circuit. Now what we did is what we find is measure the bob bits. Now after finding bob bits, what we gonna do? We gonna check the key. We gonna check the key that the key we find is correct or not. How we gonna check key? By measuring bob bases and Alice bits that we also did in the presentation I discussed before. How we gonna do it? Here is the Alice basis. Here is the bob basis. How we gonna find it? IBM pre-write it for us. Then we started a key string. We started a for loop for checking all the bits, all the qubits. Now for qubit index and I range length bob basis, we here find the bob basis length and start the for loop. Now we use if else loop in for loop for comparing. What we're gonna compare here is Alice basis equal to bob basis. If it's correct, then save it in a string key. Otherwise, continue. Then at the end, after comparing all the qubits, we will find a key. We're gonna print that key and we're gonna check that key. If the key is correct, here the message will be show is congratulations type in the IBM website. But here is not shown because it's a saved repository of us. Now, why we saved the M message? We copied it and pasted in the next tab for our convenience. We copy the key and paste it below for our convenience. Uh, Here we have to decrypt the message. The message is encoded, so we have to decrypt it too. Here, who is decrypting? Bob is decrypting because Bob is the person. Bob is the person who got the message and must decrypt it to read the message. Now M is the message key. We also find it in the previous cell. Now, what is this thing? C is equal to integer m power m comma 2 power integer key comma 2. This is a equation of XOR key. XOR XOR key. I also defined XOR key in the PPT that when same it's like 0 0 and 1 1 has 0 0 and 1 1 evaluate, then we got the answer 0, and when 0 1 and 1 0 evaluate between them, then we got the answer 1. We find the decrypted message here. All the below 3 lines were pre-written by IBM, so we don't want anything to change in here. Now we find the decrypted key. Now we check decrypted that are the pre-written function by IBM. Check decrypted like that things. So we check the decrypted key and it's good. Then we proceed to the next part of here. That's the Morse code. Now we find out that the key written here, that's not simple English. That changed into Morse code. Now from here we understand that how the message was coded. First of all, the message is written in alphabet. It changed into Morse code. Then Morse code into binary. Then he cryptographed it. He encrypted it. He encrypted the binary number. Uh, then send it to the sender. Bob receive it. Bob received a decrypted a message. He decrypted it, which he already done before. Now he changed it into Morse code, then Morse code to alphabet. The binary number here is not showing, but it was showing in IBM website. So what is this thing? Morse code. Let's see Morse code in the PPT section. Yeah. So we discussed all. So what is the Morse code? Morse code is a method used in telecommunication to encode text. It is used so that no one in between change things except the receiver and the sender. No one can see the message. It's in the form of dot dashes, which also dots is also got dates and dashes also can dash. Maybe any other language. This is a basic definition of Morse code. Now we will decode Alice message. Now let's go towards the repository section. Here. Here we got the decrypted message, but it's in the form of Morse code. Now we change the message into Morse code, binary into Morse code, then Morse code into alphabets. How we gonna change it into Morse code? We done it using Morse code translator. We copy the key, the decrypted message. The decrypted message is not print here, but it's in the repository part. We copy the decrypted message, change it into Morse code by using Morse code translator. Then we got then we got a Morse code. Morse code in the form of dashes, dots, spaces. That's how Morse code look like. Now, what we're gonna do then? We must change the Morse code into alphabets so that our message will be readable. We done it mechanically, but you can also use some Python code. How we done it? It's pre-written here. Every dot must be replaced by a one. Every dashes must be replaced by every double one must be replaced by a dash. That's how we change into Morse code. And how we change the Morse code into alphabets? We use a Morse code translator to change into alphabets. We paste the alphabets in a variable name solution, show message solution. Show message is a function pre-written by IBM. Then after pasting it in show message, our code, the website we got is also beneficial for a hint for exercise 4. Exercise 4 is the toughest exercise in this challenge. When we paste this website in a new tab, a website will open of Reddit in which it shows the hint for exercise 4. Of course, this website is not available now because it is now closed by IBM and IBM challenge has closed. But when we were doing the challenge, this website was available for us. Now, after this show message solution and all this thing, we submitted that thing and our exercise 3 was done. This is how we cryptographed a message in quantum cryptography. Now, I think I should tell something about Alice and Bob. Alice is the sender, Bob is the receiver. Alice send a message to Bob and Bob receive a message. Now, there's a question that why don't we use simple cryptography method? Why we use quantum cryptography for it? Because in quantum cryptography, if any person who is not sender receive a message and try to decrypt it, the receiver will know. Here, there's a thing in qubits that not only the value, there is a phase of qubits. If any other person other than a receiver try to decrypt it using wrong basis or wrong key, the phase got changed, and the person the sender, the receiver, sorry, the receiver will know that it was that receiver will know that someone tried to decrypt it. Now that's all for exercise 3. Now let's head towards exercise 4, which is the toughest exercise of the challenge. Now I want to share something more. This is the certificate I got after completing the IBM Quantum Challenge. This is the advanced certificate. We all 4 participants, the speakers here, got this certificate. Thank you so much. Allah is from my side. Now exercise 4 will be continued by Iqra Naz. Let me share a screen. Okay.
Okay. Hey guys, I'm back now. Okay. Let's continue. First of all, congratulations to all of you for completing the first 3 exercises of IBM Quantum Challenge 2020. Okay. So now we have challenge 4, and it was the last and most important challenge of this exercise. Okay. Uh, and it's really interesting to tell you that this exercise was about even to puzzle the quantum scientists among us. This exercise was based on the hints we got from previous exercises, as you hear earlier that Mooazam told you about reddit.com and gadget.com, and Miqdad told you about the solution string we got from exercise 1. So before proceeding to challenge 4, I want to share some definitions that we some terms and their definition that we will use in this challenge. First of all, what is circuit decomposition? Basically, in quantum circuits, we can say that a set of quantum gates is universal if we can unitarily transform quantum data from one set of gate to another set of gate. And you already know from exercise 1 about C0 gates and Hadamard gates. These gates can easily be transpiled and into another circuits, like and these forms universal gate set as well as unitarity can be implemented by using them. So our task was to form an efficient unitary matrix that can be decomposed into lesser number of quantum gates. Okay. So we have unitary matrix. Basically, unitary matrix is a matrix whose inverse is equal to its conjugate transpose. If we say unitary, then it must hold some properties, like it is invertible. Secondly, the columns of unitary matrix must form an orthonormal basis, as well as the rows of unitary matrix must also form orthonormal basis. And use isometry with respect to inner product, which were determined by U. And its eigenvalues lie on the unit circle. Okay. From here, we get to know about the term unitary. Basically, then it comes to isometry. Isometry is a transformation which maps the elements of one matrix to another metric space. Means elements of a matrix can be mapped from one metric space to another metric space in such a way that the distance between these matrix elements must be same. Then we came to transpilation. Basically, transpilation can be defined as source to source compilation. But in transpilation, the output is generally understandable by a human. And this output must have to go to a compiler interpreter to convert into machine language. So what's the difference between compilation and transpilation? You can see that compilation, the main task of compilation is to change the source code into machine language, such that in GCC compiler we take C code and as an input and produce binary or machine code as output. But in transpilation, it's a subset of compilers in which we take source code file and convert into another source code file in some other language or different version of the same language. So the output is generally understandable by the human, but it's necessary after transpilation that we have to compile it by using compiler or interpreter to change it into machine code. Then we'll use the cost factor. Here the cost factor is the most crucial to design or implement any quantum circuit, because when it comes to quantum circuit, it becomes most unavoidable part of design technique. And we use Hadamard unitary sandwich technique and it has an amazing cost reduction potential in quantum circuit. Let's see how. We will look at the C0 gates and number of U3 gates, which is Hadamard gate, to reduce the cost of our decomposition circuit. We will use only 2 gates here as we are instructed to do so. And we will determine the cost as cost is equal to 10 times of number of controlled X gates plus number of Hadamard gates. Okay. I hope you understand these basic terms. So let's move towards the main exercise of the challenge. Okay, let me share the exercise first. Okay, I hope it's visible to all of you. So I'll use my Git repository as IBM has turned off its notebooks for use now. So let's start with circuit decomposition. You all know circuit decomposition means we will have to decompose a huge circuit into smaller circuit, and then we will apply some operations on it. Okay. But in this challenge, we have some restrictions and constraints. Basically, we have just to use C0 gates and single qubit rotation means Hadamard gate. And second thing is that our unitary matrix can only be deviate from the original matrix up to 0.0 error. And the third constraint was we have to find a cost that must be less than 1600, but the lesser the better. Okay. First of all, we were given the unitary, and that was a 16 by 16 matrix, and we have to perform all the operations on our unitary matrix. We have imported all the necessary libraries and so on from Python, and then let's start with the code. First of all, we were given a unitary. You can see here, get unitary that's already defined as a 16 by 16 matrix. Then we have imported SciPy to form a Hadamard matrix. Basically, we can't use head to mud gate over here because we are using a matrix. So we can multiply a gate to a matrix directly. So used head to mud matrix. So we just got head to mud matrix by Sapper, and we imported linear algebra, and then got head to mud matrix like this way. You can see it. Then, as you know, we have hint from exercise 1 that we were given a solution string. So we just decode that solution string and turn that into ASCII codes. What we got from that ASCII codes, it was saying header. Okay, so header, we got hint that we have to use header. So we just sandwiched that unitary matrix given by IBM Quantum challenge in between two header matrices. So using NumPy, we just got the dot product of header with unitary matrix, and then again we got that product of that matrix to header. Basically, it was a type of sandwich in which unitary was in between the two header matrices. After that, we just we got a matrix that was like in many decimal points. Okay, so we just rounded it off. To round off that matrix, we just introduced a new matrix. Basically, this matrix we used here is the round off form of U2 matrix. Okay, and after that, I just added a global phase. Here I added global phase in it. Basically, C1 matrix is adding a global phase in it. You can just go and Google it, what's global phase, and you just came to know that it has very important role in these matrix transformations. So we just added global phase in our matrix, and then I just ISO and then transpile my matrix, and what I got that my cost was low enough, but my circuit was deviated more than 0.01 error. Why? Because I just multiplied these my unitary matrix with header gates 2 times. That was just changing that matrix. So to nullify that effect, I just again used this header gate. Basically, it's a header gate I used over here, and I applied it to 0, 1, 2, and 3. Basically, on my 4 qubits before ISO and then after ISO. Just to nullify the effect occurred over here. Okay. Then I transpiled my overall circuit, and I got to know the cost that my cost is 51, and it was as much lower cost as I can. So just we ended up here, and here our IBM Quantum Challenge 2020 was done. Yeah, we can reduce this cost further, but we ended up here. I hope you know quantum basics now, and you have much more knowledge about IBM Quantum Challenge, and we hope that you will explore it further and will apply for it in future. If you have any questions or any query regarding it, you can contact us. You can also contact on our club link, which will be given in chat section, and you can also get access to my repository for this code and further. And that's all from my side. Hope you all enjoyed it a lot. You can also join our group, that's Quantum Computing Club, to further explore and know about it all. And in this quarantine, you have the most better time to learn and explore something new. So stay home, stay safe, and happy learning. That's all from my side and my team. We are very thankful to all of you to join us and make this webinar the best. May Allah save all of us. Stay blessed. Allah Hafiz and happy learning. Thank you. Okay, Shahbaz, I'm making you host.
Okay, thank you so much, Iqra, for your this presentation. We really learned a lot of things from you and other speakers as well, Syed Muhammad Mooazam, Rubab, and Miqdad sir. It would be really productive for us that we join this session, and I hope that our participants also get a lot of things right now about the quantum computer. I want to say something more, that if you really want to know about the terminologies and something like exercises, challenges, and the courses, or that is about the quantum computing, which are going to conduct it on all over the websites all over the world, on the international websites like Coursera, something that you must need to connect and have a contact with us. You can join us with our on our Facebook page, or you can message us. And if you really have good knowledge of quantum computers, so you can also uh, touch with us, so that you will help us in future to make us some functioning and designing of parts of the quantum computer. I know that it's really a big deal, but when you have a high dreams and your dreams is moon, but when you miss it, even you will be a star. So we are not thinking to make a moon, but at least if we try to, we will make a star. So that is all from my side. I hope that you will make this time really productive, and inshallah in future we will, when we done many things successfully, we will also share it about. Thank you so much for being with us. Stay tuned. Allah Hafiz.